I got so much motherfucking design on right now.
Break it down, bring it back, make it clap. I got 3 old thoughts, new guap, wear that thing. Bitches on my line, and you know I got 3 old thoughts, new guap.
Hello guys, welcome to our video documentation of Hall effect practicum.
We are from group 3 in the modern physics experiment course.
Okay, first of all we will introduce our group. There are Dini, Intan, and Nia. In this video, we will conduct a practical experiment in modern physics experiment section, namely Hall experiment.
Before starting the practicum, we will discuss how the Hall effect works.
The Hall effect is the generation of the potential difference in electrical conductor, perpendicular to an electric current and applied magnetic field, discovered by Edwin Hall in 1979. This effect occurs when the charge in the conductor are subjected to the Lorentz force, causing a build-up of charge on one side of the semiconductor, creating an electric field.
Hall effect is observed in metallic and semiconductor materials. A thin metal plate in a magnetic field generates a Hall voltage. Hall effect instruments are essential for determining electrical properties such as conductor type, resistivity, mobility, and carrier concentration. If the charge carriers are negative, negative charge buildup occurs on the right side of the conductor. If positive, it occurs on the left side.
Current can be thought of as negative charge moving in one direction, figure 1, or as positive charge moving in the opposite direction. To determine the actual polarity, the semiconductor is bent in a magnetic field that is biased toward the direction of current flow. The Hall voltage measured across the conductor will be positive or negative depending on the side of the charge carrier. Equilibrium is achieved when the magnetic force equals the electric force. Of the experiment, this practical activity aims to 1. Determine the charge current density, 2. Determine the type of charge carrier, and 3. Determine the Hall constant.
4. Tools and materials. Let's start the experiment. First, we will prepare the necessary tools and materials. Here we use an experimental kit from Pasco, and the tools are 1. 2-axis magnetic field sensor, used in Hall effect practicum to detect and measure magnetic field in 2 axes. Usable for observing Hall potential change in conductor materials exposed to a magnetic field. 2. Hall effect apparatus. This apparatus may be used to demonstrate the Hall effect, which is the occurrence of a Hall potential when an electric current flows through a conducting material exposed to a magnetic field. Usable for physics experiments related to the properties of conductor materials and magnetic fields. 3. 50-150 universal interface. Sensor and software interface can be used to integrate data from magnetic field sensor in the experimental system. 4. Pasco capstone software. This software is used for data analysis of Hall effect experiment. It provides an interface to record, analyze, and visualize data generated by magnetic field sensor and other devices.
We will start the preparation of the practicum tool. The steps are 1. Connecting the electromagnet to the Hall effect apparatus using a banana jack on the part level extension current according to the guidance in figure 2.040. 2. Looking at the back of the Hall effect proof connecting the banana jack to the Hall current EI on the Hall effect apparatus for 1 and connecting the 4 label UH using the banana jack to the Hall voltage UH and the Hall effect apparatus, also according to the instruction in figure 2.4. In 3, connecting the passport extension cable PS 2500 between the two axis magnetic field sensor PS 2162 and the passport for on the universal interface 550. 4. Use the 8-pin DIN extension cable UI 5218 to connecting the port marking interface Hall voltage on the Hall effect apparatus to analog input A on the universal interface 550. Next 5. Use the 8-pin DIN extension cable UI 5218 to connecting the port market interface Hall current on the Hall effect apparatus to analog input B and the universal interface 550. And next 6. Making sure the magnetic field 2-axis sensor and Hall effect probe are at the same height and position them in the center of the magnetic field. And 7. Turn on the universal interface 550 and Hall effect apparatus. Next 8. Setting in the excitation current to reach 0. Next 9. Setting the Hall current unit in the reading 0. And last 10 step is opening the passcode chapter program and in hardware setting. Ensure that the Hall current, Hall voltage, and magnetic field sensor are unitomically detached. When all the tools are prepared, we will start the experiment.
Hall effect practicum procedure. Experiment 1. Current variation in a semiconductor with a constant magnetic field. In this first experiment, we will carry out a series of steps to understand the Hall effect in semiconductors by varying the current and maintaining a constant magnetic field. 1. Start by placing the Hall probe exactly in the center of the magnet. 2. Set the excitation current from 0 to 1000 mA and select a value of 50-100 mA to keep the magnetic field strength constant. 3. Ensure that the Hall current in the range of 0 to 10 mA is at 0. 4. Review and set the Hall current to 0.5 mA. First, keep to record the voltage and current. Next, increase the Hall current in 0.5 mA increments, pressing keep for X step until it reaches 5.5 mA. Finally, press stop and return the Hall current to 0. 5. Slide the Hall probe out of the magnet. Press the tare button next to the magnetic field sensor and insert the magnetic field sensor back into the magnetic field. Perform preview and keep to record the magnetic field strength, then press stop. 6. Set the current to the range of 0 to 1000 mA with a value of 800 mA and record the data again. Repeat step 1 through 5. 7. Remove the magnetic field sensor and Hall effect probe from the magnetic field. 8. On the resulting graph, plot the relationship between V and I.
Experiment 2. Magnetic field variant by constant current on a semiconductor. In this experiment, we will analyze the relation between the magnetic field and the current through the electromagnet. while keeping the current torque the semiconductor constant. First, we will characterize the magnetic field as a function of the current through the electromagnet by creating a table of magnetic field strength perpendicular versus magnetic current A and creating a graph that represents this relationship. In step 2, setting the half current and excitation current EM to 0 and calibrate the magnetic field sensor by pressing the tare button. Place the sensor at the center of the magnet. In step 3, the torque preview. Adjust the excitation current EM to 550 mA. Clicking keep to record the data. In step 4, after that, adjust the excitation current according to the flow in the table. Click keep for each flow change and stop when done. Make sure the excitation current is returned to 0 to prevent overheat. Next, step 5. Apply cubic curve fitting to the graph. Using the Chapson calculator, derive the equation for magnetic field B as a function of current I. B is A plus B I plus C I quarter square plus B A cubic. And the next step 6, move the magnetic field sensor away from the magnet and place the Hall effect probe in the center of the magnet. 7. Step is setting the Hall current is to 5 mA. Ensure the excitation current is 0 for 1000 mA is 0 and the setting in the sleep rank to 10 Hz. In the step 8 is the torque preview. Increase the excitation current to 50 mA and click keep. Continue increasing the excitation current from 50 mA to 900 mA. Clicking keep and time and stop when finished. And next, step 9 is the setting Hall current 0 for 10 mA to outflow of 8 mA. Then record the data again. Repeat step 7 until 11. Next, step last 10 is in the last graph. Plot the relation between fault and magnetic field.
Okay, in this table, first is electric current variation with the magnetic field and the current variation at the 500 mA and the Hall voltage variation from the minus 4.7 to minus 47. And as you can see, the graph of relationship with the Hall voltage and current straight is directly proportional. While the Hall voltage increased, then more straight the current that created. Okay, for Hall voltage variation, as you can see, there is a current constant at 5 mA and the magnet current variation from 50 to 900 mA, and the variation of magnetic field to Hall voltage create the directly perpendicular for each relationship between magnetic field and Hall voltage in the table. Okay, for half voltage variation, as you can see, there is a current constant at 5 mA and the magnet current variation from 50 to 900 mA, and the variation of magnetic field to half voltage create the derivative perpendicular for each relationship between magnetic field and half voltage in the table. Okay, for data processing, is the first one is electric current variation. Variation about the 500 mA, 800 mA, and 0 mA with the variation of the data magnetic field. Now we can calculate the slope of difference of this m, or the slope in the data graphic in the processing. We got it from experiment, and the n is carrier density, and the last one is RH is the Hall constant, and we got it to get the processes data of this electric current variation. Okay, for the second one is turn variation magnet with the point A, B, C, D, and the of the current is 50 mA. So with the calculated of magnetic field, the formula, as you can see, the A plus B times E, and the C times E quarter, and D plus I quarter 3, and then compare it the error percentage between the calculated magnet and magnet measure. Lastly, in this experiment of half voltage variation at the variation of 5 mA and 8 mA, we have to search the formula or the processing data of density carrier and the constanta Hall, as you can see the result and how the formula on it.
Discussion Hall effect experiment. By knowing the direction of the current in the existing magnetic field, we can predict the charge distribution on the slab of the metal, result in a potential difference known as Hall potential. One important application of the Hall effect is Hall effect sensor, which are used to detect magnetic field. When a magnetic field affects the sensor, the current flow in deflect, allowing detection of change in the magnetic field on the effect side. Hall effect experiment have the goal of determining charge, current density, charge, current P, and the Hall constant. And the first experiment, the current reflux through the semiconductor was varied and the magnetic field remaining constant. As a result, the magnetic field D is 0.0385 Tesla and the current S is 500 milliampere, and the flow of charge current density N is 2.45 10 second 90 C4 meter cubic, and the Hall constant RH is 0.255 C4 meter cubic, and the setting B is 0.0588 Tesla, and EM is 800 milliampere. The flow of in is 2037, and the 10 the square 90 C4 meter cubic, and the RH is 0.264 C4 meter cubic.
In the second experiment, the magnetic field was varied by changing the current flowing through the semiconductor electromagnet, while the magnetic field remained constant, with value of A 0.00660, B is 0.0800, and C is 0.00208, and 9.84 cross 10 to the minus 4 power. The compression between the calculated and measured magnetic field shows a percentage error of less than 8%. This result confirms that our experiments are consistent with existing theory. In the half voltage version, which IS is 0.005 ampere. The value of N is 0.00231 cross 10 to the 19 power and Rx is 0.00231 cross 10 to the 19 power and 270.56 at is same 0.008 ampere. The value of N becomes 0.00218 cross 10 to the 19 power and Rx is calculated as 286.669 using the formula 1. From the graph, it can be seen that the high voltage value and current strength of the directly proportional, validating the compatibility of the result with existing theory. Conclusion: load carry density 1 for EM 500 mA and 2.45 cross 10 to the 19 power. 2 for EM 800 mA and 2.37 cross 10 to the 19 power. 3 for ES 5 mA and 0.00231 cross 10 to the 19 power. And 4 for ES 8 mA and 0.00218 cross 10 to the 19 power. Chain carry type is electron or negative charge. How constant? 1 for EM 500 mA RH 0.255 and 2 for EM 800 mA RH 0.264 and 3 for ES 5 mA RH 270.56 and 4 for ES 8 mA RH 286.69.
Okay, maybe that's all our video presentation of Hall experiment, and thank you for watching. Bye bye.
I got so much motherfucking design on right now.
Break it down, bring it back, make it clap. I got 3 old thoughts, new block, where that thing, bitches on my line.